In this example, an L4 by 4 by half angle is bolted to a 5/8 inch thick gusset plate using three 3/4 inch diameter A490X bolts in a pretensioned bearing connection. The angle and gusset plate are both made out of A36 steel. The goal of this example is to determine the design strength of the member in connection considering all pertinent failure modes, and then determine the slip resistance of the connection. Failure modes it will investigate, working our way from the angle through the joint to the gusset, include gross section yielding and net section rupture of the angle, block shear of the angle, bolt shear, bearing, and tear out, block shear of the gusset, and gross section yielding and net section rupture of the gusset. As the instructions request, we'll also calculate the slip resistance of the connection as well. We'll start our calculations by looking at the strength of the angle as a tension member and calculate the gross section yielding strength of the L4 by 4 by half. The nominal strength, R sub n, is equal to F sub y times A sub g. Substituting values of 36 ksi and 3.75 inches squared, we find that the nominal strength is equal to 135 kips. And applying a resistance factor of 0.90, we find that the design strength, phi r sub n, is equal to 121.5 kips. Next, we'll look at the net section rupture strength of the angle, where the nominal strength, R sub n, is equal to F sub u times A sub e, or F sub u times A sub n. Using 1 minus x bar over L for the shear lag reduction coefficient, and substituting in 1.18 inches for the connection eccentricity and 2 times 3 inches for the connection length, we find that U is equal to 0.8033 in this case. Next, we calculate the net area, A sub n, by subtracting the cross-sectional area lost to the fabrication of one bolt hole. Assuming that standard holes are used for the 3/4 inch diameter bolts, the net area is found to be 3.313 inches squared. Substituting values of 58 ksi, 0.8033, and 3.313 inches squared, we find that the nominal strength is 154.3 kips, and applying a resistance factor of 0.75, we find that the design strength, phi r sub n, is equal to 115.8 kips. Now that we know the strength of the angle, we'll move on to determine the strength of the bolt group. The strength of the group of 3 bolts is determined based on the lesser of the shear strength of the bolts, the bearing and tear out strength of the angle, and the bearing and tear out strength of the gusset plate. I'll start off by calculating the shear strength of an individual bolt, which, at the nominal level, is taken as the nominal shear stress F sub nv times the nominal unthreaded body area of the bolt, A sub b. Note that I am using the notation lowercase r sub n to indicate the strength of an individual bolt. Later, we'll add the strengths of the 3 bolts together and then use the notation uppercase R sub n to indicate the strength of the entire bolt group. We can look up the nominal shear stress F sub nv of the bolt in AISC table J3.2, and for an A490 bolt, which is a group 150 fastener, that is installed with its threads excluded from the shear plane, we find that F sub nv is equal to 84 ksi. Next, we can calculate the body area of the bolt, A sub b, and for a 3/4 inch diameter bolt, that is equal to 0.4418 inches squared. Then we can substitute those values into our equation and find that the nominal strength is equal to 37.11 kips per bolt. Applying a resistance factor of 0.75, we then find that the design strength is 27.83 kips per bolt. The strength of all 3 bolts is the same, 27.83 kips per bolt. Next, we can calculate the bearing strength of the material being connected by the bolts. The nominal bearing strength of the base material is taken as 2.4 times d times t times F sub u, where d is the diameter of the bolt and t and F sub u are the thickness and tensile strength of the base material, which is either the angle or the gusset plate. Substituting a thickness of 1/2 inch and a tensile strength of 58 ksi for the angle, we find a nominal strength of 52.2 kips per bolt. Applying the resistance factor as 0.75, we then find that the design strength associated with the angle is 39.15 kips per bolt. Similarly, substituting in a thickness of 5/8 of an inch and a tensile strength of 58 KSI for the gusset plate, we find a nominal strength of 65.25 kips per bolt. And then applying a resistance factor of 0.75, we find that the design strength associated with the gusset plate is 48.94 kips per bolt. The bearing strength of the base material is the same at each of the 3 bolt holes. Next, we'll calculate the tear-out strength of the base material around each hole. In an effort to make this easier to understand, I'm going to show the sketches of the gusset plate and the angle separately. When we transfer a tensile load across this joint, that load can be visualized like this on each of the 3 sketches. The tension load on the gusset plate is held in equilibrium by the forces in the bolts, bearing against the insides of the holes in the gusset plate, acting in the direction opposite of the applied force, downwards as I have them shown here. Similarly, the tension load on the angle is held in equilibrium by forces in the bolts bearing against the insides of those holes, also acting in the opposite direction, acting upwards as I have shown them sketched on the slide here. The nominal tear-out strength of the base material is taken as 1.2 times L sub c times T times F sub u, where T and F sub u are again the thickness and tensile strength of the base material, either the angle or the gusset plate, and L sub c is a clear distance measured from either one bolt hole to the next hole or from one hole to the edge of the part, in the direction that the bolt force is acting on the base material. Since a clear distance can be different from one bolt to another and from one component to another, there can be several different values of strength associated with each bolted joint. Because of that, it is sometimes convenient to label the bolts like I have done here with the letters A, B, and C. We'll start with bolt A, and we'll look at the gusset plate first, where the clear distance is measured from the bottom edge of the hole to the end of the plate. Thus, L sub c can be calculated as the distance to the center of the hole, 1.5 inches, minus 1/2 of the hole diameter, which is 3/4 of an inch plus 1/16 of an inch. Thus we get 1.094 inches for the clear distance for bolt A on the gusset plate. Substituting this value into the nominal strength equation, along with a plate thickness of 5/8 of an inch and the plate tensile strength of 58 KSI, we get a nominal strength of 47.59 kips per bolt. When we look at the angle, the clear distance is measured from the top edge of hole A to the bottom edge of hole B. Thus, L sub c can be calculated as the center-to-center hole spacing, 3 inches, minus 2 times 1/2 of the hole diameter, which is 3/4 of an inch plus 1/16 of an inch. Thus, we get 2.188 inches for the clear distance for bolt A on the angle. Substituting this value into the nominal strength equation, along with the angle thickness of 1/2 inch and the angle tensile strength of 58 KSI, we get a nominal strength of 76.14 kips per bolt. When we look at bolt B, we'll start off with a gusset plate, where the clear distance is measured from the bottom edge of hole B to the top edge of hole A. Thus, L sub c can be calculated as a center-to-center hole spacing, 3 inches, minus 2 times 1/2 of the hole diameter, which is 3/4 of an inch plus 1/16 of an inch. Thus, we get 2.188 inches for the clear distance for bolt B on the gusset plate. Substituting this value into the nominal strength equation, along with the plate thickness and tensile strength, we get a nominal strength of 95.18 kips per bolt. When we look at the angle, the clear distance is measured from the top edge of hole B to the bottom edge of hole C. Thus, L sub c can be calculated as a center-to-center hole spacing, 3 inches, minus 2 times 1/2 hole diameter, which is 3/4 of an inch plus 1/16 of an inch. Thus, we again get 2.188 inches for the clear distance for bolt B on the angle. Substituting this value into the nominal strength equation, along with the angle thickness and tensile strength, we get a nominal strength of 76.14 kips per bolt. Finally, when we look at bolt C, we'll again start with a gusset plate where the clear distance is measured from the bottom edge of hole C to the top edge of hole B. Thus, L sub C can be calculated as the center-to-center hole spacing minus 2 half-hole diameters. Thus, we get 2.188 inches for the clear distance for bolt C on the gusset plate. Substituting this value into the nominal strength equation, along with the plate thickness and tensile strength, we get a nominal strength of 95.18 kips per bolt. When we look at the angle, the clear distance is measured from the top edge of hole C to the end of the angle. Thus, L sub C can be calculated as the end distance to the center of the hole, 1.5 inches, minus 1/2 of the hole diameter, which is 3/4 of an inch plus 1/16 of an inch. Thus, we get 1.094 inches for the clear distance for bolt C on the angle. Substituting this value into the nominal strength equation, along with the angle thickness and tensile strength, we get a nominal strength of 38.07 kips per bolt. The nominal tear-out strengths of the base material for each of the two components around each of the bolts are shown here on this slide, along with the clear distances. For bolted joints with regularly spaced bolts, it often works out that there are 6 different values of strength to be considered. There is typically a first row of bolts, one or more interior rows of bolts, and a last row of bolts. In this case, with a single column of bolts parallel to the axis of the angle, there is a first bolt, bolt A, an interior bolt, bolt B, and a last bolt, bolt C. This can result in 3 different strength values, and then considering that there are typically 2 plate elements being joined together, it results in 6 different strength values in total. One thing that is important to keep in mind is that when calculating the clear distance for tear out, you should not add an extra 1/16 of an inch for material that is damaged during fabrication of the hole. The extra 1/16 of an inch that is included in the calculations here is to get to the nominal size of a standard hole for a 3/4 inch diameter bolt. A standard hole for a 3/4 inch diameter bolt is equal to 13/16 of an inch. Finally, on this slide, we present the shear strength, bearing strengths, and tear-out strengths for each of the bolts and each of the connected base materials at their nominal strength levels. At this point, we can take the minimum values for the 5 strength levels at each bolt location, and as it works out, the bolt shear strength governs in all 3 cases. Finally, we can take the strength of the bolt group as the sum of the strengths at each bolt location, or in this case, take uppercase R sub n as 3 times 37.11 kips per bolt, and then apply the resistance factor of 0.75 to the design strength to find the design strength of the group to be 83.50 kips. Next, we'll calculate the gross section yielding and net section fracture strengths of the gusset plate. To do that, we often rely on something called the Whitmore section, after Richard Whitmore, who was a professor at the University of Tennessee in the 1950s and 60s. A description of the Whitmore section can be found in Chapter 9 of the AISC Steel Construction Manual, and there is a good article about it in AISC's Modern Steel Construction as well. The Whitmore section is basically an effective width of the plate that is defined by drawing lines at angles of 30 degrees from the start of the joint to the end of the joint. The Whitmore width or Whitmore length is defined where those lines intersect another line that is drawn perpendicular to the line of action of the force. Thus, in this case, the Whitmore width is equal to 2 times 2 times 3 inches times a tangent of 30 degrees, which is equal to 6.928 inches. One of the 2's is because there are 2 spaces that are 3 inches long, and the other 2 is included because there are 2 segments with lengths that are each equal to 6 inches times the tangent of 30 degrees. Now that the Whitmore width is defined, we can calculate the gross section yielding strength of the plate, which is equal to F sub y times A sub g. Substituting in values of 36 KSI for the yield stress, 6.928 inches for the width, and 5/8 of an inch for the thickness, we find that the nominal strength is equal to 155.9 kips. Applying the resistance factor of 0.90, we find that the design strength is equal to 140.3 kips. Next, we'll calculate the net area, A sub n, as the Whitmore width minus the diameter of one bolt hole, and then taking the shear lag reduction coefficient U equal to 1, we find that the nominal net section fracture strength is equal to 219.4 kips. Applying the resistance factor 0.75, we find that the design strength is equal to 164.6 kips. Next, we'll check the block shear strength, and we'll start with the block shear strength of the angle. We'll use equation J4-5 from the 2022 edition of AISC 360, and we'll use the block shear pattern defined by the lines shown here in red, representing the failure surfaces in shear and in tension. We'll take U sub BS equal to 1.0 since the stress on the tension area is expected to be uniform. The gross area in tension, A sub GT, is equal to 2 inches times the angle thickness of 1/2 an inch, or 1 inch squared. The net area in tension, A sub NT, is calculated by subtracting 1/2 a hole diameter from the 2-inch dimension and then multiplying by the angle thickness of 1/2 inch. This results in an area of 0.7813 inches squared. The gross area in shear, A sub GV, is equal to the length 7.5 inches times the angle thickness of 1/2 an inch, or 3.75 inches squared. The net area in shear, A sub NV, is calculated by subtracting 2.5 hole diameters from the 7.5 inch length and then multiplying by the angle thickness of 1/2 inch. This results in an area of 2.656 inches squared. Substituting these values, along with the tensile strength of the angle, 58 ksi, into equation J4-5 results in a nominal strength of 137.7 kips, not to exceed 126.3 kips. With that, we'll take the nominal strength equal to 126.3 kips. And applying the resistance factor 0.75 results in a design strength of 94.74 kips. If we look at the block shear strength of the gusset plate, we can observe that the tensile strength of the gusset plate is the same as the tensile strength of the angle. The gusset plate is thicker than the angle. The length of the shear area is the same for both the gusset plate and the angle. And we can observe that the width of the tension area on the gusset plate is greater than the width of the tension area on the angle, even if we were to consider the Whitmore width. With that, we can determine that the block shear strength of the gusset plate will be larger than the block shear strength of the angle. And with that determination, and since the actual width of the gusset plate is not well defined, I'll stop short of calculating the actual block shear strength of the gusset plate. Next, we'll examine the slip resistance of the connection. The slip strength of a bolt is calculated using this equation, where the nominal resistance is equal to mu times d sub u times h sub f times t sub b times n sub s. Mu is the coefficient of friction of the surfaces in contact. We'll assume that the fang surfaces of the connection meet the definition of Class A, which in the 2022 edition of the AISC specification is defined as unpainted clean mill-scale surfaces, or surfaces with Class A coatings on blast clean steel or hot dipped galvanized steel, whether as galvanized or hand roughened. D sub U is a multiplier that reflects the fact that most bolts are actually installed to a pretension that is higher than the minimum specified pretension. We'll take D sub U at its default value of 1.13. H sub F is a reduction factor when there are multiple fills used in the joint. We'll assume that there are no fillers used in this joint and take H sub F equal to 1.0. T sub B is the minimum specified pretension for the bolt. This is found in AISC table J3.1, and for a 3/4 inch diameter A490 bolt, which is a group 150 bolt, the minimum specified pretension is 35 kips. This connection is a single shear connection, thus it has one slip plane and N sub S is equal to 1. Substituting these values into the equation, we calculate a nominal slip strength of 11.87 kips per bolt, and for standard holes, the resistance factor is taken as 1.0. And thus, for the bolt group, we calculate a design strength of 35.60 kips with respect to slip. However, this connection was not designated as a slip-critical connection, so this slip strength will not be compared on par with the design strengths for the other limit states that were considered. Finally, this slide shows a summary of the design strengths associated with the pertinent limit states of the angle, the connection, and the gusset plate. As you can see, the governing limit state is that of bolt shear, bearing, and tear out with an associated design strength of 83.5 kips. Also, this connection was designated as a bearing type connection, so slip doesn't need to be considered as a primary design consideration. However, since the bolts are pretensioned, we could expect the connection to carry a load of 35.6 kips before slipping into bearing. All right, that brings us to the end of this example. Thanks.